Hello. In this video, I would like to tell a little bit about similarity and comparisons and how to use similarity and comparisons of well-known functions to find limits of sequences and sum of series. Okay, and sometimes we just need to consider convergence of a series. All right. So what is about similarity at infinity? Okay, so when we're talking about similarity at infinity, like for polynomial, if you have polynomial, then you have px equal to a0 x to the n plus a1 x to n minus 1 plus so on plus an, right? We say, yeah, this polynomial is similar to a0 x to the n at infinity. This happened at infinity. Why? Because at infinity, those terms, x to n minus 1, x to n minus 2, and so on, are very small with respect to a0 x to the n, because n, is the highest degree in this polynomial, right? And that is the degree of this polynomial. So when x approaches infinity, x to the n approaches infinity faster than any other, terms in here. So that's why we say, yeah, the behavior of the function px is very similar to the behavior of a0 x to the n. So basically, I picked the term with highest degree in here, right? Okay. And how about comparison, right? Comparison. Here I would like to compare three functions. The first one is ln of x, right, to any power p in here, and with polynomial x to the m, okay, in here, and e to the x. So what does it mean? That means logarithmic function approaches infinity slower than x to the m, right? X to the m. I write this form means, x to the m at infinity is very big if you compare with ln of x to any power p. And at the same time, any polynomial x to the m is very small with respect to exponential function. You can, instead of e, you can consider like, 2x or ax where a is greater than 1. Any exponential function, approaches infinity faster than any polynomial. So, we use this comparison and similarity to find limits of sequences and then and to consider convergence of series. Let's consider the following example. Let's find the limit of the following sequence, ln of x to the 4, not x to the 4, but n to the 4 over 3n, right, when n approaches infinity. We know that for each sequence, we can find the corresponding function, right? Let me write out that corresponding function. So the function of this sequence looks like ln of x to the 4 over 3x, right? And find limit of this sequence means, find limit of this function when x approaches infinity. So that is nothing but to find horizontal asymptote of this function. Is that correct? We can use L'Hopital rule for this problem, right? We can use L'Hopital rule. Let's say I need to find limit of function ln of x to the 4 over 3x, x approaches infinity, but ln x to the 4 means, just 4 ln of x, right? And here we have 3x, x approaches infinity. When you plug infinity into this limit, you get infinity over infinity. So when you see something like that, you would think about L'Hopital rule, okay? So if you differentiate, right, I will use L'Hopital rule. I will find the limit of 4 ln of x derivative over 3x derivative when x approaches infinity. If this limit exists, then our limit right here equal to this limit, right? So let's differentiate this. I get on the top just 4 times 1 over x, because the derivative of ln of x is 1 over x, divided by 3, right? X approaches infinity. So when you simplify this, you get, let's say 3, 4, we'll take that out, and then limit of 1 over x, x approaches infinity, and this is just 0. So that means this 0 is this limit. So basically the limit of our function is 0, right? So that means the limit of this sequence is also 0. But this is, an application of L'Hopital rule. All right, now let's use comparison. Okay, let's use comparison. I say, at infinity, ln of n is very small if you compare with n. So then we have limit of ln of n to the 4 over 3n, n approaches infinity, equal to limit of 4 ln of n over 3n, n goes to infinity, and that is 0. So, that is simple. This is some kind of very similar to L'Hopital rule, but we don't have to use, differentiation in this case. All right. We can take another example, right? Let's consider another example when we can use L'Hopital rule. Let's find the limit of the following sequence: n squared over 2 to the n minus 1 when n approaches infinity. Of course, you can solve this problem using L'Hopital rule by just considering limit of function x squared over 2x minus 1, right, at infinity. And of course, you plug x equal to infinity into this, you get the form infinity over infinity, and then you can, use L'Hopital rule. But I don't need to use that. I would say on the top we have polynomial n squared. In the bottom we have 2n minus 1, which is exponential, right? So I can write at infinity, n squared is very small if you compare with 2n minus 1. But 2n minus 1 is similar to 2 to the n. Because, at infinity, 1 is nothing, right? So the behavior of 2n minus 1 and 2n are almost the same. So I can write, 2n minus 1 similar to 2n, and n squared is very small with respect to 2n. So the limit of n squared over 2n minus 1 when n approaches infinity is 0. Okay, so that's how we can use similarity and comparison to solve limits of sequences. Now let's talk about convergence of series, right? And how to use similarity at infinity and comparison to consider convergence. Let's consider the following series. Series n from 1 to infinity, an over 4n squared plus 1. Okay, so the general term of this series for an over 4n squared plus 1. On the top you have polynomial of degree 1. In the bottom you have polynomial of degree 2. So at infinity I would say 8n over 4n squared plus 1 is similar to an over 4n squared, which is 2 over n. What do I do in this situation, right? I just ignore all terms, with with degrees less than 2, I just pick the term with highest degree in here. Let's say this. The term with highest degree is 4n squared. Right, and then, since 4n squared plus 1 is similar to 4n, this guy is similar to 4n squared, right? So I just write 4n squared in here, and then I have an over 4n squared. I simplify and I get 2 over n. And of course, we can say then, the series n from 1 to infinity, 8n over 4n squared plus 1 is similar to n from 1 to infinity, 2 to the n. And this is harmonic series, right? 2 times 1 over n. And I will say P in this case 1, right? P in this case 1. What is P? P is the power of harmonic series. Okay, let me remind that. So harmonic series looks like 1 over n to P, n from 1 to infinity. That is harmonic series. So in this case, we have P equal to 1, and we know that harmonic series, converge if P greater than 1, and diverse for P less than or equal to 1. So this is just equal to infinity, which is diverse. This is how we can use similarity at infinity to consider convergence of this guy. All right. In the textbook, you will see very similar technique, which is called comparison, right? But I will not use this in here because that is, in my opinion, that's more difficult because you have to find another function which is similar to your function right here. Okay, so I say, yeah, let's use comparison. Okay, or let's use, similarity. All right, let's consider another example. In this example, you need to find OP for which series converge. Find OP for which the series converge. Okay, so your series look like this. And from 1 to infinity, n over 2 plus n squared to P. All right, so again, I will use similarity at infinity. So this series is similar to the following one, n from 1 to infinity, n, right? And in here, I just pick n squared because I ignore 2, right? I just pick n squared because that is the term with highest degree. So I have, that is just n squared to P, right? Which is, infinity, and 1 n in here, and here I have n to 2P. And let's simplify n, I get this series equal to n from 1 to infinity, and then 1 over n 2P minus 1. Again, this is harmonic series, right? And we know this is harmonic. Harmonic series converge if the degree 2P minus 1 greater than 1. So we know that, right? Greater than 1. So solving this for P, we get P 2P greater than 2, and then P greater than 1. So that is all P for which the series converge. All right, you see, it's very easy, right? If you understand this, philosophy, so everything is good. All right, so let's talk about one more thing, which is also, important in this topic, geometric series. Geometric series. So series look like, n from 1 or from 0 to infinity, r a to the n. So or you can write that is just r a to the n, and from 1 to infinity. Okay, we know this. We know this series converge. I'll write here converge if absolute of a is less than 1, right? If absolute of a is greater than or equal to 1, diverge. So let's consider the following example. Let's say I'll say it looks like 1/6 to the n. Well, let's say just 1/6, right? Okay, without -1, let's say that. And then, okay, let's pick -1/6. And then n from 1 to infinity. Okay, this is geometric series, right? And a, in this case, equal to -1/6. And when from here I get absolute a is just 1/6, right? Which is less than 1. So from here, we have that the series converges. All right, now our problem is to find sum of this series. So we know the formula, even, for geometric series, we know the exact formula of this. So what is that? I will not, I will not do computation. I just write the formula right away, okay? The formula looks like, sum n from 0 to infinity r a n equal to r over 1 minus 8 equal to r over 1 minus 8 when absolute a is less than 1. Okay, that is our formula. So the index, pay attention that index runs from 0 to infinity, okay? But in our series, index runs from 1 to infinity. So how to adjust this? It's easy. Let's do this. I write sum n from 1 to infinity, -1/6, right, to n. It's just equal to n from 0 to infinity, -1/6 to the n, right? So we add one more term, which is corresponding to n equal to 0. Since we add that, we have to subtract, right? Minus -1/6 to 0. But this term is, just 1, right? This term is just equal to 1. So I write here, using the formula right here, okay, I can find the sum. In this situation, r is just equal to 1, right? So that is 1 over 1 minus -1/6 minus 1, because this is just 1. So I can do this easily. Here I have 1 over 1 plus 1/6 minus 1, which is in here I have 1, 7/6 minus 1. And then, I flip this, I get 6/7 minus 1, which is -1/7. So our series is -1/7. So I hope that this video is useful for you to prepare to test or quizzes. Thank you for watching.